Hello dear friends, welcome to my channel. Today's discussions is Hermitian operator. Okay, so in the last couple of videos, we have been working with observable and the representations as linear operator within our vector space. I want to introduce Hermitian operators and show you how they connect to our physical observable. As a heads up, make sure you have watched observable videos since we will using results derived in that chapter. To begin, I want to introduce some slightly new notations. We have worked with the following expression a lot. This is just acting the operator m on the ket phi. Because m acting on phi returns another vectors, we also commonly write this as this is just a ket representing the vector we would get when we act m on phi. Okay. So when we have an inner product expression, okay, this is inner product. Okay, this is inner product expression that look this. It's sometimes convenient to write like this way. This equals to can be written this way: psi m phi. Remember, this is just the inner product with psi and m phi. So with that, here's the setup and a geometric intuitions. Say we have this inner product. Remember that the inner product is basically the dot product. So let's rely on that for some intuition. This can be written the following expression that this way: cos theta. Okay. Remember that we have the following equivalent expression for the dot product. So geometrically, this inner product basically says act m on phi and then measures the new angle between the new vectors and psi scaled by their lengths. Okay. So friends, in here psi means psi. We can say this. It is the scalar scaled by their length. Scaled by length, and m phi can be said act on m m on phi. Okay, so act m on phi. The measures the new angle between the new vectors and psi scaled by their lengths. Okay, now here we want to investigate, do we have an operator n that we can apply to psi instead and give an equal inner product. Okay, so if we see that geometrically, whatever I say, that act, okay, this way, if we just, just draw this equation. Okay, 1 minute. Okay, this way I can. Okay, so this is called psi and this is called phi. So it can be written as m act on phi and scaled on. Okay, this is the psi. Okay, so so we have an operator n that we can apply to psi instead and give an equal inner product. So whatever I want to say, I want to say that the inner product psi m act on phi can be written as n cap psi phi. Okay, this way. Now geometrically we are asking if we have an operator that allows us to instead move psi and still give us the same magnetic times angle of the two vectors, and this must be true for any two vectors phi and psi that we choose. Okay, whatever the geometrically you can see that this way geometrically. So this is called n kit. Okay, n cap psi and this is phi. Okay, so this way we can write. Now this operator is called Hermitian adjoint. Okay, it turns out there is such an operator. This operator is called Hermitian adjoint. Adjoint, we designate the Hermitian adjoint by taking our operator and adding a dagger to front of it. Okay, we can say dagger. This way we can write dagger. Okay, this is our dagger. So the fundamental properties of the Hermitian adjoint is that it satisfies the following properties. Okay, it satisfies the following properties. Okay, psi m act on phi, okay, equals to Hermitian operator m plus psi phi. For any vectors phi and psi, now there are few properties of the Hermitian adjoint that I want to show you, but their proof is not very enlightening. However, I encourage you to practice bracket notations, means Dirac notations. I encourage you to practice Dirac notation. So now I will discuss property of the Hermitian of operators. Operators number one. Hermitian adjoint of Hermitian adjoint is the operator itself. So Hermitian adjoint of Hermitian adjoint is the operator itself. Number two, the Hermitian adjoint of a sum is the sum of the Hermitian adjoint. Number three, the Hermitian adjoint of a product of operators is calculated by switching their order and taking the individual Hermitian adjoints. What is the Hermitian adjoint of a scalar? Okay, what is Hermitian adjoint by scalar? So we can set up an inner product with the scalar number as the operator C dagger. Okay, this is the dagger. Okay, so we can set up an inner product with the scalar number as the operator. This is the inner product. We want to know how to move this scalar to the other side of the inner product. Well, we can pull the scalar out of the right side of the inner product since the right side is linear. Then we can remember that the left side of the inner product is antilinear. So we have the complex conjugate, the scalar to move it into the left side. Therefore, we have that the Hermitian adjoint of a scalar is just the complex conjugate. That is C plus is equal to C star. Okay. This is an important fact that you should remember. What is the Hermitian adjoint of a cat? Okay, now this might seem like a weird question since we have been considering a cat as a vector, not an operator, but bear with me as we try to make sense of it. Instead of working with the cat by itself, let's work within an inner product. This is the inner product. Okay, bra act on cat shy. Okay, so what is the Hermitian adjoint of an inner product? Okay, now the questions is not cat, it is inner product. Just remove this. Inner product. So I can write this way. Okay, so well, an inner product is just a number, so we get the complex conjugate which just flips the inner product. So it can be written as this way: I shy star, and this is the flipped. Okay, so we can write this way: shy phi. Okay, so but we can also evaluate the Hermitian adjoint of the inner product by first breaking up our inner product. Breaking up inner product by first breaking, okay, adjoint of inner product by first breaking up our inner product and using our rule for adjoint products. Okay, so we can write this way: phi and break this portion. This can be written this way: break this and shy. Okay, so again I repeat that we can also evaluate the Hermitian adjoint of inner product by first breaking up our inner product and using our rule for adjoint products. We switch the position. Okay, then take the individual Hermitian adjoint. So we can write this way: okay, so and this way. Okay, switching the position. Now this expression, the one we previously found, must both be equal. Okay, so it can be written this way: psi, okay, psi and phi. Okay, this way it can be written. Yeah, okay, this way it can be written. So since phi and psi are both completely arbitrary, this seems to point that the fact that Hermitian, so the fact that ket psi Hermitian is equals to bra psi. Okay, adjoint of ket is a bra. Okay, and the Hermitian adjoint of bra is ket. Now this is more of a justification rather than the rigorous proof, but this really is true in the description. How do Hermitian adjoints connect to quantum physics? Okay, well, we can ask ourselves, what is the Hermitian adjoint of an observable? So this is the questions. What is the Hermitian Hermitian of an observable of an observable? Okay, so this is the very great questions. So we can write this is the observable. Okay, so let's go over what we know about observable so far. Remember that we found that physical observable are represented by linear operations whose eigenvectors represent definite states and eigenvalues represent corresponding measured value. Okay, so you should remember this portion, that definite state. Okay, definite states means, remember that we found that physical observable are represented by linear operations. Okay, it is okay, and whose eigenvalues represent definite states and eigenvalues represents corresponding measured value. So we can write this way: this is called definite state. Okay, night state, and this is measured value. Okay, observables must also follows rule from our physical intuitions. Recap, recapitulate in our previous videos. Okay, recap, this is the, that when if you watch observable, then you must know that eigenvalue must be real. Okay, number one, eigenvalue must be real. Okay, number two, span of eigenvector. Okay, span of eigenstate. Okay, you can say eigenstate equals to dimension of the vector space. Okay, the eigenvector vectors must span the whole space, since each quantum state must span the whole space, since each quantum state must carry some value for the observable. Okay, number three, ei is equal to del ij. The eigenvectors must be orthogonal, otherwise they would not be definite states. This last two allows us to conclude that observable have an orthonormal eigenbasis. Given these properties of observable, I want to show you an incredibly useful way to express observables that will be helpful in finding the adjoint. First, let's consider our observable acting on arbitrary constants, quantum state. So observable acting on quantum states, psi. Since this operator has an orthonormal eigenbasis, we can expand our quantum state in this eigenbasis and move the operator into sum. Okay, so that I want to say that E cap Ci I divided by E I. So we can expand our quantum state in the eigenbasis and move the operator into the sum. So just move the operator. So we can write this way: psi I, capital E cap, okay, ci, and operator ei. Now next, it can be written this way, and e can be written this way: I and c ei. Okay, since these are eigenvectors, the operators will just give us corresponding eigenvalue. So we know the coefficient by the Born rule. Okay, I will explain what is Born rule, okay, in my videos. That ei psi, we can get the coefficient, and this can be written, these equations can be written summation. This is my result. Okay, summation I ci can be written this way. Okay, 1 minute. So putting the coefficient value, so we get ei psi ei ei. Okay, we can move the inner product over to the right. So we can move, so we can write move. So ei, this portion, okay, ei and ei psi. Okay, now using the power of bracket notation, we can break up this inner product. Now just I just use the bracket notation: ei ei and ei, just okay, use the power. Okay, since psi is the same of every term of the sum, we can pull it out. So we can pull it out. So I can write this way: summation I ei ei ei. Okay, just pull it out. Okay, this way I can write. Okay, so e psi can be written this way. Okay, psi means eigenstate, so ci ei. So this value can be written e cap psi. Okay, so we found that the action of the observable on any psi is the same as the action of the sum of operators. In other words, they are equal. So e cap can be written psi I ei. Okay, this way we can write. So we have found that observable can be written as sum involving their eigenstates and real eigenvalues. If we have an observable with a continuous eigenbasis, we can follow the same logic. So when it is continuous, then we can write this way: not sum, it is the dx and x. This way it can be written. So let's use this form of observable to see what their Hermitian adjoints are. So what the Hermitian adjoints are is this property I used. So because my discussion observable Hermitian, so it can be written this way: summation. So let's use the form of observable to see what their Hermitian adjoint are. will do the discrete case here, but that the logic is the same in the continuous case. First, let's use the property that the Hermitian adjoint of a sum is the sum of Hermitian adjoints. So, we use this property. So we use this property. Now we can write this way that I is equal to EI and EI. This way we can write. Okay, so let's use our product rule for the Hermitian adjoint. We flip the order and then distribute the dagger. The Hermitian adjoint of a bra is Kate, and adjoint of the Kate is a bra, and the adjoint of scalar is the complex conjugate. So we can write this way. So that we get this is Hermitian Kate as a bra. So we get this way, and the complex conjugate equals to, we can write this way, summation. Okay, so remember that the eigenvalues have to be real, since this represent the outcome values that we can measure. So this just gives us the same eigenvalue. We can move to back to left, and since it is scalar, and check it out, we get the exact same operator back. So we have just proved that the Hermitian adjoint of a physical observable is itself. So we can write this way. Okay. So physical observable is itself. We have special name for operators that are their own Hermitian adjoints. We call them Hermitian operators. Well, observable is Hermitian operator satisfies following inner product property. Okay, since we deal with observable all the times in quantum mechanics, this property is really handy. So it's worth remembering. So friends, whatever we learned, let's discuss that observable is equivalent to adjoint of, okay, okay, E is equal to E cap, okay, span of EI is equal to V. Okay, so observable equals to Hermitian operators. You have to remember it. Okay, so equivalent to e cap, and span ei equal to v, and eij. So this portion is remembering, I have already written eij is equal to del ij. Okay, and every ei is real. Okay, every observable operator is a real values. So friends, I hope I can clear and I give some idea to you. And now you will check my total work. I just try to please check my total work, and I think that it is very best explanations that everyone can understand what is Hermitian operator. Thanks for watching.